So today we are doing our second sort of discussion about this linear programming method, which we started talking about last time. So today we'll see a full version of a proper linear programming question. So last time we kind of did a bunch of preparation for it, but today we'll actually see the full process and then what the kind of the goal or the value of it is. So last time, the visualizing problems. So if we have codependent variables, more of X means less of Y and vice versa. And we want to find, well, what's the best combination of these two things relative to some third thing like profit or cost, then we can put that on a graph and look at it and see how to see the solution visually, not just with systems of equations. And then today we'll add another kind of layer to that. All right, so homework, feedback. I posted a whole thing about this, but lots of people lost points for question 1 because the question said use substitution and people didn't use substitution. Question 2 is supposed to be using matrices, and lots of people, some people did not use matrices or had no labels on their matrices. You would have lost some points for that. Matrix, it's nice and organized, but you need some sort of indication of what operation you are doing so that other people can look at your work and follow it. There were a lot of people who seemed to just get kind of confused about the whole matrix process, or like they got kind of partway through and didn't seem to know how to continue. So matrix elimination, it's still just elimination the same way we would do with a system of equations. So at any point, if you're confused or sort of stuck, you have your matrix with whatever values, then just imagine or actually rewrite it as a system of equations, something X, something Y, something Z, like this. And then with that system of equations, what would you do for elimination as the next step? What would you try to eliminate? And then exactly that is what you can do with the matrix. The matrix looks different, but it is actually the exact same process. So that's if you understand the elimination process, then matrix elimination shouldn't be much harder than that. Normally we would write comments and feedback. For the matrix stuff, it seemed like it wasn't just like, oh, here's this one bit that you were a bit confused about. It was like a lot of kind of larger scale issues, hard to just write, like address with a single comment or something. So for question 2, I recorded a video of going through the whole solution that's posted now on our YouTube playlist. If you're confused about the matrices or how to do them, I encourage you to look at that. Question 2 didn't need to be too hard. So after the first matrix, after just rewriting as a matrix, there were just 4 steps. I don't quite have space to write 4. So just 4 additional matrices, and that's the solution. 2 going down to the triangle form, and then another 2 to get the sort of final just main diagonal form. So that video, that solution is up. We've gone through a bunch of questions in class and in the workshop and everything, but if you want one more example, then that's there. I'm gonna guess that a lot of people, the feeling that I got was a lot of people just didn't actually try any of the review questions I recommended, or they didn't do any of the, even if you don't attend the workshop, at the minimum, I would say, look at the list of questions recommended for the workshop or that will be done in the workshops, and then go through those. That's the minimum amount to know that you've done at least some practice and you're reasonably familiar with how to do the questions. The homework questions are not going to be like the easiest possible one. I do expect you to have gotten a basic understanding of how to do these questions, and then the homework's going to not be like way harder, but a little bit more. So do some other practice questions before you attempt the homework questions. All right, so also just that kind of thinking, that kind of preparation, very good preparation for our exams. The exams are not going to focus on the easiest possible questions. They're going to expect you to have a good general knowledge, and then you can kind of apply that to a slightly trickier situation. Last bit, I wish this wasn't happening, but still lots of people who didn't like do the PDF file, the scanning, or combining into a single file, or very unclear handwriting. Some work, especially if you're doing the substitution stuff, like just having kind of arrows pointing all over telling us what the next step is, like this, that doesn't work. Like a nice like organized column or something. If we need arrows to be able, lots of arrows to follow your work, then it's probably not very organized. If we have to guess at what your process is, then we won't. We'll just say, okay, I'll just kind of imagine that this part is blank. So we need to be able to follow your thought process to see that you understand it. The same way that I, write out enough process for you to understand the work during class. If I just jump to, here's the final answer, you figure it out, that wouldn't be very useful. So I show you the process so you can understand what's happening. I expect you to do the same and have a clear enough process that other people can read it and understand what your thought process was. So more feedback is written on the classroom page, the video's there as well. If you check that and you still have questions, then definitely please come ask. You can send me a message or book time to talk with me during office hours or whatever, and we'll go through that. But please take a look at that. The next homework next week is going to be on the two topics that people tend to find hardest, at least for the midterm: linear programming and then matrix multiplication, which we'll get to next week. So the next homework is going to be a bit harder. Please make sure you're actually doing some review questions and such so that you'll be prepared. Okay. Let's go on with today's material. So last time we looked at this problem with the students selling laptops and phones, and here's their profit for laptops, profit for phones, and they want to know, they had these two different goals for profit. And what we asked was, how can this person maximize their profit? Not just, can they reach this one? Can they reach that one? Rather than testing individual possible profits, we want to say overall, what's the maximum profit? So we did this, we turned the situation into this graph, and we talked about a bunch of things here. Let's sort of review some terminology. So first, the orange line here. This was representing the kind of limits and how far she could go. So she can't produce more than what's in that, over that orange line. What is our fancy term for that line?
Constraint line.
Constraint line, yes, thank you. So there, constraint line. Constraint again just means a limit. So we also, from the constraint line, we can figure out what this area is that shows all of the different possible solutions. What's our name for that one?
Feasible region.
Blue area.
Okay, feasible region. Feasible meaning possible. So that's the area showing all the different combinations of X and Y that could work. And then if we want to figure out which one is the best, we have these two lines here that show all of the profits, all of the ways, all the combinations of X and Y to get a profit of 3,000. And this other one showing all the ways to get a profit of 4,500. What's our fancy name there?
ISO profit.
Okay, so ISO profits lines. ISO, again, meaning same. And later we will have ISO cost lines and ISO revenue lines and ISO whatever lines, whatever we're trying to optimize. So isofunction lines is our more general term. Okay, those are the terms and just the labels that we'll be using as we discuss this. So next, let's actually talk about our solution here and how we figured this out. So we probably remember that point D we figured out was the best one, but let's just repeat the description of why. So first, a point like C, which is here in somewhere in the middle of that feasible region, it's not on the constraint line. Is it possible for a point like C to be the best solution?
No. No.
Why not? Why could something like C never be the best point?
Because it's not even on the constraint line. So it's not the maximum number that can be sold.
Okay, so in this case, it's number that we have time to sell. So we haven't even pushed all of our inputs, like time available to do this. So if we haven't gone to the limit, we haven't used up all that we have available, then okay, clearly we're missing something. If I only tell 80% of the workers in my factory to work, and the other 20% aren't doing anything, that's a pretty big waste. So she has extra time she's not using in this case. So points like C in the middle of the feasible region will never be the best one. Okay, next, what about B? Is a point like B, can it be the best solution here? So in this case, it's not on any kind of corner, it's just somewhere in the middle of the constraint line.
No.
Why not?
Because if you take any other point that's above B, there is a way to go to the limits towards A. That's why it cannot be the best. Or if we can take any point below B, which is going to the, again, the number which is higher than B, it can be the better solution. That's why we can take B in the middle as the best solution.
Okay, so good. That's the basic idea. I'll just give another explanation of that. So let's say we have point B and we figure out it's whatever profit here. So it's in the middle of a straight line. So basically we could imagine, what if we went kind of up to the left or down to the right? Let's say we go up to the left and the profit, we test any point that's up to the left and the profit there is lower. So it's a straight line. So if one step going up means that our profit decreases, then 2 steps will mean it decreases even more, and 3 steps even more. So any step in that direction will give us the same, it'll be an equal sort of degree of decrease for each step. So it won't be the case that 1 step will give us a lower profit, but then 2 steps gives us a higher profit. If we had a curved line, okay, maybe a point in the middle could be the best. But this is a straight line. So straight line, one direction, it's going down. So forget that direction. We don't want to go down. And in the other direction, well, one step in that direction gives us a higher profit. So keep going. Don't stop somewhere else in the middle. Keep going until we hit the end. That will give us the best possible one. So in a general problem, we don't know which direction that would be. So we consider the corners. In this problem, there are only two possible points where we could have the highest possible profit. Excuse me. A or D. Forget everything else. Forget the whole inside of the feasible region. Forget all the other points in the middle of the constraint line. We only care about the corners. So just from this graph and a little bit of logic, we can eliminate almost all of the points that are possible here, almost all the combinations of X and Y. And in this case, we only have 2 points to look at. Some later problems will have a few more, like 3 or 4 points to look at, but it's much better than having hundreds or thousands of points to test. So this is just having a graph, being able to understand it, that's much better than having to say, well, is this profit possible? Okay, test that one. Is this one possible? Test that one all individually. This is a much kind of smarter solution. Okay, so corners, but which corner? A or D? So the way that we figure that out, again, we probably remember it's D, but let's understand the logic behind that. If we have these two profit lines, 3,000, 4,500, in which direction does profit increase?
Perpendicular.
Perpendicular to what?
To those lines, isoprofit lines.
Okay.
Closest to the isoprofit lines.
Right. So perpendicular to these isoprofit lines. This is the direction in which profit goes up. So we can look at A here and say, well, A is a little bit relative to these arrows. It's a bit below the 3,000 line. D is a little bit above the 3,000 line. So clearly D is going to be the better one. So if we want to think of this a slightly different way, again, just turn the graph in your head, and then it's hopefully a bit clearer that if we compare A and D, D is sort of higher relative to, again, perpendicular line like this. The way that we actually solve these linear programming questions is usually we would do this. We would just draw one isofunction line, isoprofit line that's close to, but not touching our feasible region, like this. And then we just look at each corner and we imagine a perpendicular line like this. So that's 1 for A, and that's 2 for D. Which line is shorter? We just look at the graph and we see visually which one gives us the shorter line. Okay, A is clearly, the line from A to the isoprofit line is clearly much longer than the other one from D. So D is the better choice. D is closer to that isoprofit line. Therefore, it is more quote unquote up in this direction, the direction of the arrow. So D is our best choice. We only had 2 corners to consider. Now we've eliminated and we figured out that it's D. Okay, so that's the logic behind it. That's why that is the best solution. And then a little bit later, we'll extend that to a more complicated version of this problem and then see what our best solution point will be. So for now, let's just mostly a review from last time. For today, we'll just kind of take a step back and look at some common situations and some common shapes that we often get with a linear programming question. And then we'll go back to that question we just saw and look at a more complicated version of it and figure out what our solution would be there. So we're going to do some graphing here. We have this system of inequalities and this system of inequalities, which are both will give us sort of a common shape that we would see. And then we'll also graph these two things. So some isofunction lines, iso profits, and then iso cost lines, just to look at them and understand, again, common situations that we see for linear programming, and then we'll put them all together with the example at the end. So let's start here with this first one. We want to graph this thing here. So let's say we have this as our feasible region. These are we look at a problem and we turn it into math and we get these, and then we want to graph these. So each of these are in standard form. What's the easiest way to graph these?
To use, find the exponents, right?
To find the intercepts.
Intercepts. Okay, so the x-intercept and y-intercept. We could change them into the slope-intercept form, but I definitely think finding the intercepts is a lot faster. So what are the intercepts for this first one?
X 4.
X is 4 and
Y is 5.
Y is 5. Okay, I'll just repeat how we find that, and then we'll do the other ones a little more quickly. So x-intercept happens when y is 0. So 0 times 4, that's just going to disappear. What are we left with? So I know this is less than or equal, but first we draw just the line, then we do the shading. So we imagine that it's just 5x equals 20 to graph the original line. So 5x equals 20, so x is equal to 20 divided by 5, 4. Like, we don't really need to write that out. We can just kind of do that in our heads. All right, next one, x and y intercepts.
X is 2 and y is 6.
2 and 6. All right, and the third one?
X is 3 and y is 7.
X3, Y7. I did have a little trick here where I put the Y's first and the X second, and I'm glad that didn't fool anyone. And then these last two here, these are our kind of non-negativity constraints. So we understand that those are there. Basically, that's telling us when we shade, we're not going to shade over with the negative X values. We're not going to shade with the negative Y values, because for our whatever problem this is, just negative values don't make sense. So it's good to include that in the math to just say that we won't be going there. All right, so we have intercepts. We can graph these. So our first one, 5 and 4. So here's our blue line, our red line is at 2 and 6 here, and our green line at 3 and 7 there. Okay, so shading is next. For each of these, are we shading above or below the lines?
Below.
Below the lines. So because this is a less than or equal, if we were unclear about that, we could also just consider the origin points. So 4, 0 plus 5 times 0 less than or equal to 20, 0 less than or equal to 20. True statements. So origin point must be included. So we must be below here. All right, so below the blue line and below the red line, they are all less than or equal, and below the green line. Okay, so those are the shaded regions for each of these inequalities individually, but what we actually want is the shaded region of the three of them combined. What's the area where all three of them, excuse me, are true? So I'll write some labels here, and then you can tell me which one you think is the best. So let's call this area here number 1, this one number 2, this one 3, this one 4, this one 5, and then this final area up above everything we'll call 6. Which one represents the solution to the system of inequalities?
6.
6. Can you explain why you think so?
Because in any label you give, there is no common sharing point with the red line. Even in the fourth one, which is closer. That's why I thought it was 6.
Okay, so the region 4 does not include the red one. I agree. So region 4 would not be our best solution. Does anyone else?
3 maybe.
Yeah, 3.
1.
I think it's 3. I think it's 3.
Okay, everyone else is saying 3. So let's evaluate these one by one. So region 1 includes the green shaded area, but not red and not blue, because red and blue are below that. Not going to be 1. 2 includes red and green, but does not include blue. So that's not all of them. 5 here only includes blue. It's missing the red and the green. 6 doesn't include any of them. So that's a bad choice. The final one is just 3. That's the only one that includes the shaded area for all of them. So that is our solution space. This pink area here. So erase those. That is the area showing possible solutions here, number 3. Okay, looking at this pink shaded area now, how many corners do we have?
4.
4. Can you tell me where those corners are? What color is meeting what other color or what axis?
Yeah. The point where blue color meets with the red one.
Okay, so let's do a different color. Try again. Okay, so this point here where red and blue meets, that's 1 corner. What else?
The y-intercept.
With y-intercept of what?
Of 5.
Okay, so the blue, where the blue line meets our y-axis, that's the second point. What else?
X-intercept of the red line, 2.
Okay.
And 0, 0 point.
And 0, 0. So those are the 4 corners. The shape has 4 sides, so 4 corners. When we do a linear programming question, the solution will never be 0.00. If we're trying to maximize with something like this, you're not going to get the maximum whatever when you do nothing. When you, like in our previous example, sell 0 phones and 0 laptops. So like in terms of geometry, we understand that, yes, that's a corner, but also in terms of linear programming, we understand, no, that will never actually be the solution. So often when we talk about these, we're just going to kind of forget that origin point. But yes, in terms of geometry, it is a corner. So if we were trying to solve this, then we would say, okay, one of those 3 corners, that's our best possible spot. So let's consider those 3. Okay, so this is a pretty standard shape that we will have for a maximization problem. So we'll go from the origin and then include kind of up and to the right a little bit, but then we'll have some sort of bound like this, and we'll have some sort of ISO profit or ISO revenue line or something like this, and then, okay, which corner is the best one? So this is a common scenario we could see. I forgot to mention this earlier. So we might just notice the green inequality here. So the green line, our third one, it didn't actually impact anything. So it's not actually changing our solution at all. Even if we didn't have that one, it doesn't change the shape that we are ending up with. So it would turn out that in our problem, that constraint, that inequality ends up not really having any impact. So either way, you'll still get the same shape and the same corners, but it can be sort of useful to kind of be aware of that. We thought that we had this thing limiting what we could do, but it turns out that it didn't actually impact anything because the red one was even more limiting everything. Okay, so just a little side thing we can notice. Let's look at another example that will be a typical minimization problem. And we'll see an actual full minimization problem in our next class, next week. So our X and Y intercepts, let's figure out those for each of these, X and Y. And we'll switch colors here. So for the first one, 2x plus 5y greater than or equal to 15, what are the intercepts?
Three and 7.5.
Okay, so our first one here for the X, it is, sorry, my colors match, 7.5 for X and then 3 for Y. For the second line, second inequality, what are the intercepts?
3 and 8.
3 and 8. Okay, so very convenient where if the constant 24 is equal to the two coefficients, 8 times 3, just multiplied by each other, then the intercepts here will just be those two coefficients just flipped. So very nice little pattern we can notice there to figure that out more quickly. The last one, pretty straightforward. These are just going to be 6 and 6. Okay, let's graph and see what sort of shape we get here. So Y of color matching, Y3 and X of 7.5. That will give us this. Our next one, pink at 8 and 3 here. And then our last one, 6 and 6, like this. All right, for each of these, are we shading above or below these lines?
Above.
Above for all of them because they are all greater than or equal. So above the purple one, above the pink one, and above the orange one. So I'll do the same thing that I did last time. I'll write some labels here and then you can tell me which one you think is the actual solution to all of these. So region 1, 2, 3, 4, 5, 6, and then this whole big top area, 7. Which one is the total solution here?
7th.
So say that one more time.
7, 1, 7.
Okay, why 7?
Because it's like everything is greater than our answers, we can say, the variable, like the equation is greater than that, so every single area is lifting up to that one.
Okay, so everything is above, so
Yeah.
it's kind of common sense. Okay, it has to be the highest possible one. We could also think just process of elimination. Region 4 doesn't include any of them, so can't be 4. Region 5 is only the pink one, not purple and orange, so not that one. Region 6 is missing the pink one. 3 is missing the orange one. 2 is missing 2 of them. 1 is missing the pink one, so 7 is what we're left with. So our total solution space for this is just here, and then off to infinity, way over just all of this. All of these are possible solutions. So in case this feels a little weird, this is what a typical minimization problem looks like, where we have like a minimum order. We must produce at least this many things, and we have some sort of labor contract. We must pay our workers to do at least this many hours, and we have some sort of supply that we're trying to use up because we don't have space in our warehouse. So we have to use at least this many units of whatever thing. But despite all of these things forcing us to do more and spend more money, we are still trying to have the lowest possible cost. So things are trying to push us to spend more, but we want, within that limitation, we want to find the lowest possible cost. And that's going to give us a graph that looks like this for a minimization problem. So this is another common kind of situation that we see with these styles of problems. Okay, so that's just corner points, I forgot. How many corner points do we see for this shape?
4.
4. So where are those points?
The one where the pink line meets with the orange one. The one where the purple meets with the orange one also. X-intercept in 7.5.
Okay.
And y-intercept in 8.
All right. So these are the 4 corners. We kind of understand that our shape goes way off to infinity. So like maybe we have some corner point at infinity or whatever, but that's clearly not going to be our solution. We can forget that. We have these 4 points. One of those 4 will be the minimum possible cost. And then we do the rest of our linear programming thing and we'll figure out which of those 4. So we'll have a problem like this that we looked at in the next class next week. Okay, so 4 corner points. So a benefit to this graphing method, this whole linear programming method, is that if we just looked at the system of inequalities, so we use our logic from before and we know it must be a corner point, but which corner point, which kind of intersection? With these 3 inequalities here, we basically would have 10 different points. We would also have points here and here and here and here and here and here. So before we make the graph, we don't actually know. We have 10 different things that could be the solution. Which one is it? And then after we make our graph, we can eliminate those and say, okay, it's actually just 4 possibilities. So shrinks it down a lot and then use our iso cost line and we can eliminate down to 1. Otherwise, we'd have to do systems of equations and elimination and calculate the profit at 10 different points. And that sounds like a lot of extra work. So there's a nice kind of efficiency that we can get doing this graphing process. All right, let's switch over to some ISO whatever line. So ISO profit line first here. Okay, I want to graph this. We are being asked to make 2 isofunction lines based on this profit equation. Can we graph this line right now?
No,
Why not? What's missing?
because we don't know the profit.
Okay, so we don't have a constant. We need some kind of constant here. So point number 2 that students often get very, very confused about when doing these linear programming questions is when we need a constant for our objective function, we make one up. We just choose a number. The constant just moves the line up and down. What we really care about is the slope. The slope is given by the coefficient. So we're not changing the slope. We're just kind of sliding the line up and down. So we can kind of freely choose a number that we want, something that just A, makes the math easy, and will just give a reasonable sort of area, like it makes sense given the scale of our graph. So let's say we choose a really easy number like 24. And if we do 24, what are the X and Y intercepts?
2 and 1.
2 and 1. Okay. And then if we graph that line, we are going to get 2 and 1. So it's this tiny little thing off here in the corner. If we consider the scale of our graph here, excuse me, then that's not really very useful. We want something that's going to be kind of in the middle of our graph where our other inequalities and stuff are. So I don't really like that one. Let's try to choose a better point, a better constant here. Can someone?
72.
Sorry, one more time. Can you suggest a number?
72.
72. I think that would work. Let's go
240.
a little bigger and we can make the math
40.
even easier for us. So
48.
240.
48 would still be pretty small. Let's get lines that are going to be somewhere kind of in the middle of our graph here. So 240, that works. Can someone suggest another one?
288.
120.
Easy math.
120.
Okay, there's no reason to like, I know the number that you chose is a multiple and it would work,
Yeah.
but there's no reason to make it harder. Just choose really easy numbers that you can like instantly graph. Can someone give me one more here?
$144.
96.
Okay, how about maybe halfway between these two? That seems like it's just really easy, quick mental math to do. So let's say 180. I think that will work out. So, all right, let's start with the first one, 240. What are the intercepts going to be with that one?
X will be 20, Y will be 10.
All right, 20 and 10. All right, those look like easy numbers to work with. The other intercepts?
10 and 5.
10 and 5. Okay, and then, didn't need to erase that. So the last one, please don't say anything. I'll just tell you how we can get them. So look, if we go from 240 to 120, that's half, right? Look what happens with the intercepts. Half.
They become
and
lower.
5, half. So it's just, we just scale. We only really need to calculate the intercepts here once. And then whatever our scale is, then we can work with that. So our third one here, 180, is halfway between 20. So it's halfway between 240 and 120. So the X will also be halfway between these two. It'll be 15. And then here, looks like we're going to have 7.5. So just choose one where the math works out nicely, and then just do some simple scaling, double it, divide it by half or whatever. There's no reason to make it more tricky for yourself.
Professor.
Question?
Yeah, X is 20 and Y is 10. How come that? How did you identify that? Just a guess number or?
We are not guessing, no. I explained that earlier. So if I want to know what the x-intercept is, the x-intercept comes when y is 0. That's the definition of it. So when y is 0, this term here disappears. 12x equals 240. So 240 divided by 12 is 20. That's the math we're doing in our heads. I didn't write out the algebra because it's simple enough. Same thing in the other direction. The y-intercept, x value is 0. So 240 divided by 24 is 10. Okay, so let's graph these. First one, y10, x20 will be here. 10 and 5 here. My Zoom controls are kind of blocking things. I have to count up. Okay. And so we have 7.5 and 15, 10, 11, 12, 13, 14, 15 there. Okay, so here are these lines. What do we notice about these iso profit lines?
That one, the first one with just 20 and 10
Perpendicular.
are better because we have another 0.8, if I'm not mistaken. Last time we had the constraint line 8, which was on the same.
We have no
They are
constraint lines here.
perpendicular.
They are parallel.
Okay.
Oh, parallel. Sorry.
Parallel, yes, that's the main thing I wanted us to notice. Again, I told you the slope comes from the x and the y coefficients. The constant does not change the slope. So we just kind of freely made up some numbers for the constant. All it did was slide them up and down. It doesn't change the slope. The slope is the thing that we really care about. So that's why making up some numbers here is okay. So the purpose of the constant is just to put the line on the graph and we can see what the slope looks like. So this is a profit situation and we want profit to be maximized, probably. I don't know, maybe you want to minimize it in some case, but we want to maximize. So then our profit is going to increase perpendicular to these lines. So this is the direction that our profit is increasing according to these arrows. So if we say, let's choose some random points here. Let's say here, I'll take this point and we'll call this A. And here's another point, we will call this B. Between A and B, which one has the higher profit?
B.
B has the higher profits. They're both like sort of level or flat relative to the y-axis, but relative to these green arrows, these perpendicular arrows, B is higher. So B has the higher profit. A and B like this. Now which one is better?
A is closer.
A, it's closer. Again, we can say, let's just imagine little perpendicular lines like this. Which one is shorter? A is shorter. The one from A is shorter, so that's the better one. What about a point like this one? If this is our B, which one gives us the better profit?
B is closer again.
Both have the same profit.
These both have the same. So we might be able to kind of see that from the grid. Also, the slope, it's negative 0.5. That's the same slope that we have for the iso profit lines here. So these two, if we made these perpendicular lines, then these would actually end up being the exact same. If we had this in a real problem and we had two corners that looked really, really similar, then okay, we just do our final calculation, what's the maximum profit for just these 2 points, and then figure out which one is the best. But this visual solution will give us, usually it will tell us here's the best spot, or if not, it'll say, okay, it's one of these two, and then maybe we just do 2 calculations, but it's better than like 10 for 10 different corners. Okay, so let's do one more of these, a little quicker this time. So here we have an iso cost situation, and we will try to graph this. So we need x and y intercepts. Please tell me, so 3x plus 4y, we need constants. Please suggest a constant that makes the math easy and makes sense given the scale of our graph.
12.
Okay, 12 will work. 3x plus 4y equals 12. I want 2 more.
24.
Okay, 24, just double 12, looks really
And
easy to work
18.
with.
No, 60. No.
Tell me another one.
18.
18. Okay, 18 could work. 4 and 8. I think we could have gone a bit bigger, but that's all right. Those points will work. So intercepts for the first one.
4.
4, 3.
4 and 3. And then if I look at the next one, it's 24. Everything's doubled. So just 8 and 6. And then 12 to 18 times 1.5. So that's a 6 and a 4.5 like this. All right, this is going to be a little small. I guess we could have had some bigger ones, but we'll still see the pattern with these. All right, so 4 and 3 and 8 and 6 and 6 and 4.5. All right, there are 3 ISO cost lines representing 12 and 18 and 24. Okay, so if we imagine a perpendicular line, which would look like this, perpendicular, which direction do we want? Which one is more desirable? Do we want to be kind of going up to the right or down to the left?
No, down to the left.
Why?
Because the lower the costs, the higher the profit that you can get actually.
Right. So it's a cost function, ISO cost function. Usually we want our cost to be low, so we want to go down to the left here. So still perpendicular, but just the other direction along that perpendicular line. So just we have to remember the context of whatever the problem is, whether we want to be going up or be going down here. So down, lower with respect to these arrows. So this is another common sort of situation. With an ISO cost line and we want the lowest possible one. If an actual linear programming question with something like this would usually end up looking like, if we have the example, the second, the minimization style example, maybe we have our feasible region ends up looking something kind of like this. And then here is our constraint lines, and then our feasible region is like this. And the corners, can't see the top corner, but there's a corner way over here on the right. Which one of these is lowest? Okay, well, we just make our perpendicular lines and another one here. And then we would just say, which one is shorter? So in this case, it looks like this point here is a little closer. We'll look at an actual proper example with real numbers again in our next class. But these are another common scenario that we'll kind of see a bunch when we do linear programming. Okay, let's actually do one of these properly. Let's go back to the original problem that we had. So I've added a little thing to it. This is the laptop phone example. So just take a moment and read the extra little bit here, and then we'll talk about it. All right, we still have the rest of this the same. We have our selling time constraint. So x plus y must be less than or equal to 50. We have these non-negativity constraints. We can't sell negative x phones or negative x laptops or negative y phones. That doesn't make sense. So we say, okay, x, y cannot be less than 0. But we now have another wrinkle, another problem that we're adding here. So this person has a limited amount of repair time as well. So they have to use some fancy electronics workshop to actually do the repairs. That makes sense. If you're going to tear apart a phone and fix it, you probably need a bunch of fancy equipment. So she only has 20 hours available in this workshop. Before, it was pretty obvious if our selling time is equal for laptops and phones, but for laptops we earn more profit, then the answer is pretty easily just, okay, do all laptops, so we get a higher profit there. But now we see that in addition to that, laptops take twice as much time to repair. So now what is it? Is it going to be still all laptops, or do we switch and do all phones, or is it some combination of the two that will give us the highest profit? So let's take that new problem, that new limitation, and let's try to write that out as an inequality here. Can someone suggest what that would be?
Yeah.
Okay, go ahead.
We have to add another kind of inequality for the repairing time. It is 30 minutes, like for laptops. We can still make it x, can we?
Yeah, we need to still use the same variables, x and y. So tell me what the
30x plus 15x is equal to 1,200.
Okay. So first of all, you said equal?
I'm sorry, less, I mean,
Less than or greater than?
greater than or equal. Less than or equal, all right.
Why? Tell me why you think it's less than.
No, it's not less than, I guess, teacher, because she should have at most 20 hours.
Okay, so you've given us your ideas, you're not sure. Can someone else tell us, should this be less than or equal or greater than or equal?
Less than or
Less
equal
than
to.
and equal.
Okay, why less than?
Because she has a limit of 20 hours per week
Yeah,
it's
she
limited
can work
time.
less
or
than
per
20.
semester, sorry.
She can't work more of like the time that is given.
Okay, so this is a limit. She only has 20 hours of access. If it were greater than or equal, that would mean she must spend at least 20 hours. But instead we have a situation where she can spend less than 20 hours is fine, exactly 20 hours is fine, more than 20 hours is not okay. So the other kind of issue we had here is that we have different units, 30 minutes and 15 minutes, but then 20 hours. So we do need to do a conversion to make sure we have the same units. What was suggested was that we convert the hours into minutes, so 1,200. That works. I think it's a little easier to think about this the other way. Let's convert the minutes into hours. Our numbers will be a little smaller. That's also what I used on the next slide, so I'm gonna adjust it to that. So if we take 30 minutes to hours, that's 0.5, and 15 minutes at 0.25, y less than or equal to 20. Both of these would work. If we graph them, we would get the exact same line, but excuse me, we would get the same line, but I'm just going to adjust it here just to make the numbers a little smaller and easier to think about. So now we have two inequalities, and let's put the second one on the graph and then see what happens, see what situation we get. Next, there you go. Okay, so we have this new one. If we try to graph this, we have the original one graphed, our x plus y less than or equal to 50. But let's also do this for our second inequality here. What are the X and Y intercepts?
40
Hmm,
and 8.
And 80.
80, okay.
80.
Good. So just it was someone might have gotten confused here. 20 divided by 0.5. That's so 20 over 1 over 2. So that's the same as 20 times 2. So that's where we get the 40 from. All right, we'll put that on our graph. Sorry, 1 second. I need to cheat and look at the next slide so I remember the color. Purple. Okay. Purple line. So from 80 to 40 here. Okay, so now we see that our feasible region, and we are shading below this purple line here. So like this, because it's a less than or equal. So basically what that means is our feasible region has now shrunk. We have to remove this whole red area here because it's under the orange line, but it's no longer under this purple line. So our feasible region has to change to reflect that. So this is the actual situation that we have now. So for this shape, how many corner points do you see?
X50 with the orange one.
Okay.
And then here where the intersection.
Okay, so intersection of the
80.
purple and orange.
50 again.
This one here?
Yeah.
Is that a corner point of our feasible region?
No, 40.
No, 40 is. So 50 is a point of intersection. If we just looked at the system of inequalities, we would have to consider that. And we would also have to consider this 80 up here. But now that we've thrown it on the graph and we see what the feasible region looks like, now we can say, okay, the orange and X intercept at 50 there, that can't be a solution because it's not in the feasible region. And this 80 up here for the purple line can't be a solution. So we have 3 intersection points that we care about, these 3 corners of the shape. So one of these 3 is our best one. So we'll label these A, B, C here. Okay, so what's the next step? How do we figure out which one's the best?
The distance from the isoprofit line.
Okay, isoprofit line, and we measure that distance with a perpendicular line. Perpendicular line here and one more. If you remember 3 weeks ago in week 2, we had that whole thing, and even in the preview question, how do we figure out the shortest distance from a point to a line? And then we said we make the perpendicular line and calculate the length of it. This is exactly why we did that, because this is the way to find the shortest distance like this, very important concept. Okay, so the line from A, line from B, line from C, which one looks shortest?
B.
B, okay. So this is the final point that people often get confused about with linear programming. We actually are getting this solution just visually and looking at it. Which one looks shortest? And I'll explain in a bit. There are more things we can do to be more certain and do some verification with algebra and all this. But the basic idea is we put it on a graph and look at it and say which one looks closest. So let's pretend here that A looks really far away, so it's definitely not A. But let's say we're not sure. Is it B or is it C? Which one is the best? So I will draw a line here and then show you something. Okay, so we have a what we can do is we can choose a new constant for our isoprofit line. Instead of 4,500, just choose a different number, choose a different constant, and that will shift the line, a smaller constant, that will shift the line closer. So basically, I'll do this visually, but what we would be doing with math is just taking our isoprofit line and just sliding it closer like this. Okay, which one's closer, B or C? Not sure, not close enough. Let's keep going closer, B or C? Not sure. Okay, now it's really obvious B is going to be the closest one. The constant we choose for the isoprofit line doesn't really matter, because a bit later, we'll actually calculate what's the exact profit for B. We'll use some algebra to verify that. So the constant is just so we can slide this line back and forth and find the closest points, or yes, find the point that's closest to our isoprofit line. The isoprofit lines are parallel, so the closest point is always the same. It doesn't matter where this line goes. The closest point will always be the closest point, no matter what our constant is. Again, because they're all parallel to each other. Okay, so this is what, I can do this because I'm drawing this on a computer and I have this line drawing tool. If you were doing this on paper, what you could do is just draw one isoprofit line and then put a ruler on your page and just keep the same angle and slide the ruler over. If you're careful with it, then that'll work. Again, I know that sounds maybe like sloppy or not like proper math or something. We'll verify that using some other stuff, and I'll show you in a moment. But that's a way of that where you can just do this kind of sliding thing. Okay, let's say we don't want to do that. We think that's just not really a careful way of doing it. Then instead, we can sort of zoom in on our graph like this. I know if you're on paper, just lean in or something. And let's say instead of 4,500, we change our constant here to be, say, 3,500, which will give us a line that looks closer like this. And then now if we compare distance from B to this isoprofit line and distance between C and this isoprofit line, okay, B is closer. So B is the better point. That's the one that we want. That is how we will get our maximum profit. Okay, so the question was asking us, what is her maximum profit? Have we answered the question?
Not yet.
Not yet. So we figured out it's B. Oh, there. But we didn't actually figure out what is the location of B? What are the exact coordinates? And then also at B, what is the maximum profit? That's what we should be doing to kind of finish up this problem. So we'll do that right now. So we figured out it's B. B is our best spot. So where is B? Well, in this case, we can just very easily look at our graph here. 30 for X and 20 for Y. So the coordinates are 30, 20. So that's the exact location of where the best profit is happening. We haven't figured out the actual profit yet. If we can't see this point of intersection, we can't see the exact numbers on the graph perfectly, then we have this system of inequalities here, and we'll just take this and reimagine it as a system of equations equals 50, because we're not less than these constraint lines. We are right on the constraint line. So we're actually on the line. So it's equals, not less than or equals. And 0.5x plus 0.25y equals 20. And that's a system of equations with 2 equations and 2 unknowns, it's pretty easy to solve that system. So we could just do some very quick algebra here. What's the x, what's the y, and then we would get these same results, 20, 30, and 20. Okay, so that's how we can find out the exact, once we have our best corner, that's how we can find the precise location, either reading it off a graph or with a bit of quick algebra. The intersection point will always just be of 2 lines. So it's just a 2 equation system. It's not going to be especially tricky to solve. So we'll head back to our setup here and our original everything. So here's the location of the highest profit, but how can we finish the problem?
Multiply the average profit for laptop and phones.
Okay, so here we have this equation 75x plus 50y that tells us exactly what the profit will be for whatever combination of x and y. So we'll just put in our numbers, 75 times 30 plus 50 times 20, and that equals
2,650.
one more time.
2,650. 2,650.
I think it's a little bigger than that.
$3,250.
Okay, 3,250. So that's a 1,000 there. 75 times 3 is 225. So add a 0, 2,250. Okay, add them together and we get 3,250. So there is our solution. So maximum profits is going to be $3,250. And so like if you're doing this analysis for this student, like, okay, that's nice, I can earn that much money, but how do I do it? Okay, do it by doing exactly, all right, let's write this out as laptops, repair and sell exactly 30 laptops and 20 phones, and that will give us the maximum possible profit. So here's the best solution and here's how to get it. This is kind of the final answer for a linear programming question like this.
But this is the best solution, taking into account the fact that she spends 30 minutes on repairing a laptop and 15 minutes on repairing a phone.
Right. So this is, if selling time were the only constraint, if that were the only limitation, we'd want to do all laptops. But now we have these 2 limitations. So we also have this limited repair time. So now when we consider these 2 constraints together, this is the best solution. 30 laptops, 20 phones. So it's not all laptops, it's not all phones. There's the sort of just right balance of the 2 that maximizes it. Okay, so that's what a full linear programming question looks like. We'll have at least 2 constraints, 2 kinds of limitations, system of equations, and then lots of graphing stuff, and we'll solve. So I've been kind of talking through the process and the logic behind it a whole bunch. So I have that written here. I'm not going to reread the whole thing, and we've been talking about that all day today. You can take a screenshot of this or come back and look at this again in the recording a bit later. So variables, identify variables, and then we put everything on the graph. I can hear someone taking pictures. Put everything on the graph and then find our feasible region and our corners. Then we have our objective function, our iso whatever line, and find the corner that's closest. And then just do a bit of quick work and figure out the exact location of that corner and whatever cost or profit we get. So that's the process. These are all the fancy terms that we use, so constraints and feasible region and corners. Some textbooks or some places, they'll, instead of corners, they'll call them the extreme points. I think that name is a little bit silly, so I'm just calling them corners. We have our objectives, which will be some sort of shown with some kind of iso whatever line, iso function line. So iso profits if we want to maximize profit, iso cost if we want to minimize cost, iso time or whatever the thing is that we're trying to maximize or minimize. And the result, we get this optimal solution. So the best possible solution. Again, with this X and Y, we had hundreds or thousands of possibilities, different ways we could have combined X and Y. So it's not a single solution situation. There are lots of solutions, lots of combinations that work, but we want to find the best one of those. So it's a nice kind of simple example of an optimization problem. All right, this slide is just, again, explaining the logic behind why corner points are the best. We talked a whole bunch about this, so I won't read this again. All right, so visualizing problems with two codependent variables. So it's more complex than just our kind of profit, revenue, costs, our TR, TC thing, because that only had one thing that we are producing. So this is more complex, and we have, again, this sort of balancing sort of problem, but we can solve them. We put them on the graph, we saw the visual everything, and we got a solution to it. Next time, we'll do a minimization problem to see what it looks like when we kind of flip everything. And then on Thursday next week, we'll have our more complex maximization problem that we can solve. So we'll get to all of that. As I've mentioned before, our main textbook is not, it's not an economics textbook, so they don't have anything about linear programming in particular. Lots about systems of inequalities, but not about linear programming. So I added that extra thing, the extra PDF file on the classroom page. It's chapter 2 from there, readings here again. I know linear programming can feel confusing, and we have done the whole process, and I have shown you the whole thing, but you still might not quite yet be feeling comfortable enough to try these on your own. If you are, then these review questions at the back of that book, chapter 2 there, has a whole bunch of practice questions that you can try out. In today's workshop, I will be going through, I have 3 planned. Hopefully we have time to actually do all of them. They do take a bit of time, so we'll see, but I'll go through some of those in today's workshop, or if you want to try these a bit later after we do more examples next week, then that's up to you. But as I said before, these kind of harder concepts, they're only going to make sense to you if you actually try to do some review questions before the next homework, before I give you the next homework question, so you've prepared for it. So at some points, I will strongly recommend you try some of those. All right, there is a preview question. I didn't write it out here, but it's on the classroom page already. You've probably seen that. We are going back to matrices next week as well. We're going to see a whole different way we can use and think about matrices and some operations about addition and multiplication and what you think those would look like. So the preview question's up. Take your best guess at what you think it would look like if you add 2 matrices or if you multiply 2 matrices. And then we'll talk about the process behind those in the next class. All right, we're a bit over. If you have questions, hang around and ask. If you lost some points on the homework, take a look at my notes and everything and the sample solution video that I posted. If you have more questions, then please ask. We want to make sure you understand that stuff and you're able to do well on the midterm. Okay, thank you for listening, everyone. Enjoy your weekend. See you Tuesday.
Thank you very much. Bye-bye.
Thank you, Professor. Bye-bye.